All right, everyone. As promised, this is a video that goes over the study guide for the unit test. So assignment 1.10. All right, question 1. It says factor each polynomial. So we've got x to the 5th plus 3x to the 4 plus 2x to the 3. And to factor this, let's take out a common factor. The common factor is x to the 3rd. And so now we have x squared plus 3x plus 2, and we can continue to factor that as x plus 2x plus 1. So now, how do we graph this? Well, our first step is finding our zeros, the values of x that make 0. So -2 will make a 0. -1 will make a 0. Let me actually push those back further. So -2 will make a 0, -1 will make a 0, and what about that? Well, what that is, I could rewrite this as x minus 0 cubed, and now it might be a little bit easier to see that 0 itself is a 0, right? Because if I plug 0, go back to the original equation, if I were to plug a 0 in for x, then that would also make the equation go to 0. So 0 itself is a 0, meaning a number that makes the y value go to 0. Okay, so now when we look at these, this is a regular root, so nothing special there. This is a regular root, and this right here is a triple root. So let's review for a second what the different roots do. This is called multiplicities. So just as a review, a multiplicity of 2, if I have x minus 2 squared, then it's going to be like this. Or if you approach it from the different side, it might be like this. You don't know on the outside, it just depends where it is in the context of the polynomial. Let's do another multiplicity. If I have x minus 2 cubed, then it's going to look like this. It's going to approach 2 like that. And so you have that. Again, depending on the context of the polynomial, you might be approaching like that, but it flattens out in the neighborhood of 2. Okay, so third roots flatten out, and we have, going up here, we have a third root here. So right here, it's going to be something like this, or it's going to be something like this, depends on the context. Now, another thing we should review is the overall end behavior. And this is something that you might want to consider just jotting down and having handy for future reference. If you have x to the even, let's just make this table. X to the even, x to the odd. And you have positive coefficient, negative coefficient. Okay, x to the even is going to be something like this. If it's positive, it's going to be a smiley face. If it's negative, it's going to be a frowny face. Now for our odd friends over here, it's going to be like this, or it's going to be like this. Okay, so let's give some examples of each just so we really know what we're talking about here. This would be something like 3x squared. This would be something like negative 6x to the 10th. This would be something like 5x to the 7th. This could be something like negative 6x to the 11th. And of course, they could have other stuff after them, but the other stuff will not affect the end behavior. Only the leading term will affect the end behavior. Okay, so again, evens are smiley faces or frowny faces. Odds wiggle up or wiggle down. And if they're negative, then it's going downhill. So think about like a negative line, y equals negative 2x, then it's a line going downhill. Okay, so let's put all of that back together with this question. So overall, this is x to the 5th. So that is a odd degree, and it's a positive coefficient. So we're expecting the overall end behavior to be like that. So when we approach this first root, we're going to be approaching it from down beneath. It's going to go through this. Now, how do we go through that 0? Again, that's a triple root, because as a triple root, we're going to come up here, we're going to flatten out, and then we're going to continue on like that. Okay, let's do the next one. Now that we have all the background in our mind, let's do this next one a bit faster. Negative 2x cubed plus 2x squared plus 24x. We're going to factor out a negative 2x. And that's going to give us x squared minus x minus 12. Now we're going to factor this further, x minus 4x minus 3. And so our roots are going to be at positive 4, positive 3, and what about that? Well, let's rewrite this as x minus 0. And that is just going to be a plain 0. Don't let the fact there's a negative 2 here confuse you. When x is 0, if I were to substitute a 0 in right here, that 0 gets multiplied by everything, the whole thing would turn into 0. So x being 0 would be a 0. That negative 2, well, what's that negative 2 doing? That negative 2 is a scalar. So it would be like this normally, but a negative 2 will make it bigger like that. Okay, so let's draw this. Let's go back to our notes here. This is negative 2x cubed. So negative 2x cubed, negative 2x cubed, it's going to be this kind of situation because it's odd and it's negative. So you have a downhill kind of thing. So our overall end behavior for this thing is going to be like that. Do we have any special roots? Nope, that's a single root, that's a single root, that's a single root. And so it just goes through normally, 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 and that is our graph. Okay, next one. We've got negative x to the 5 plus 4x cubed. And that, let's factor out a negative x to the 3rd. I like to factor out a negative x or a negative because that keeps this more in the form we're used to seeing. Okay, we have a difference of squares, x minus 2, x plus 2. So let's do our graph here. We've got roots at 0, at negative 2, and at positive 2. Now let's go up here and see what our thing is. It's negative x to the 5, and so our overall behavior is going to be like that. So do we have any special roots? We do. That guy is a 3rd root, so I'm going to make a little reminder here. That guy is going to do something special. Okay, so because the overall end behavior is like this, I'm approaching this first root from above, so it's like that. This one, I'm going to be approaching it like this. And, oh, no, I'm not. I'm going to be approaching it like this. And now because this is a triple root, I'm going to be coming, flattening out, up, and then down again. Okay, so those are all the problems for question 1. Let's move on to question 2. Question 2 is just knowing a couple things. And once you know a couple things, it should go fast. You have 5x to the 6 minus 2x cubed minus 5x minus 1. And for this whole question, you can actually ignore this and ignore this and ignore this, only focus on this. Now, what's the question asking? It's asking, number 1, the maximum number of extrema. Now, extrema, what does that look like? Well, first of all, let's think of what a 6-degree polynomial might look like. It could go like this, 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 and back up again. And if this was my x-axis, then it could look like that. Let's just put a little y-axis here. Now, of course, the graph might not look like this. This is the most number of extremes, meaning highs and lows, and the most number of intercepts drawn this way. So here we have a low, a high, a low, a high, a low. If we count them up, we have 1, 2, 3, 4, 5. Now that will be 1 less than the degree. So the first part of this question is the number of extrema is going to be 5. There are 5 extremas. The second part is the maximum number of real zeros. You can have 1, 2, 3, 4, 5, 6. And again, that will be the same as the degree. Okay, so just to recap, the extrema are 1 less than the degree. So here the degree is 6, so the extrema are 1, 2, 3, 4, 5. And then the number of real zeros is the same as the degree. That's a 6 degree, there could be 6 zeros. Of course, for this one, there could be no zeros, right? If I drew the x-axis down here, the whole thing would be above the x-axis. And then finally, the end behavior. The end behavior says, as you go left, what happens? As you go right, what happens? So let's just get rid of some of this extra detail. So let's just draw this x-axis like this. And over here, we have infinity. Over here, we have negative infinity. So as we go to the right, as we approach infinity, as I trace along this line, I'm getting closer and closer to infinity. And you notice as I get closer and closer to infinity, my y value starts to approach infinity. And so as x approaches infinity, the y value approaches infinity. Meanwhile, if I go on this side, and I'm going left now. How do I write going left? To say going left means I'm approaching negative infinity. So as I'm going left, what's happening to my y values? I'm getting higher and higher. My y values approach infinity. So that's the end behavior for that. Okay, let's go on and do the next one. You've got 2x to the 7 minus x to the 4 plus, we don't really care what those are. We're focusing on this. That's a 7th degree. Number of extrema is 6. Total number of real zeros. Total possible is 7. And the end behavior, because this is to the 7th, then we would say something like this. As we go right, let's actually write it in the same order on your paper. As we go to the left, we go down. As we go right, we go up. So you have negative infinity, positive infinity for your y values. Okay, another one really fast. Negative 7x to the 4th plus a bunch of stuff. Focus on this. Number of extrema is 3. Maximum number of zeros is 4. And the end behavior, this is to the 4th, so it's an even. Evens are like this or like this. But that negative, right, if you're in a negative mood, you're sad, that negative makes it a sad face. So then you end up with this thing right here. It's a sad polynomial. And as you go this way, you go to negative infinity. As you go this way, your y values approach negative infinity. So your y values approach negative infinity on both the left and the right. Okay, graphing some polynomials. This should go kind of fast since we've reviewed this already. X minus 1 cubed. We're on question 3, by the way. X minus 1 cubed, x minus 2, x plus 3. Okay, so let's plot our zeros. We have 1, 2, negative 3. Negative 3, 1, 2. And this guy is a triple root, so something interesting happens there. The rest are normal roots. Now, what is the degree of this polynomial? If I was to multiply this polynomial out, then I would end up getting x to the 5. Now, where am I getting that 5? This would be x minus 1, x minus 1, x minus 1, x minus 2, x plus 3. If I multiplied all of this out, I would have x times x times x times x times x. That's where the 5 x's are coming from. I know the polynomial will start with 1x to the 5th. Also, look at these guys. This is 1, 1, 1, 2, 3. And it's going to end in 6 or negative 6. Now what happens in the middle is going to be a whole bunch of difficult combining like terms and working things out. But the first term of the polynomial and the last term, there won't be any combining like terms. So we can already see through this polynomial that it's going to be a 5th degree polynomial. Okay, so because it's a 5th degree polynomial, then let's think about the end behavior. It's 5th degree, it's positive, it's going to be like that. Okay, so I'm going to go up and I'm going to go here. Now what happens in the middle? I can't just cross it like that because this is a 3rd degree. It's a multiplicity of 3. So I'm going to approach it like this and like that. So it flattens out around that neighborhood. Okay, let's do another one. Let's do this one a little bit faster. We've got negative x squared, x minus 2 squared, x plus 1. What's the degree? We have 1, 2, 3, 4, 5 x's. So it's x to the 5. We have a negative, so negative x to the 5. Its overall behavior is going to be like that. We have zeros at 0, at positive 2, and at negative 1. So when we graph this, we're going to, let's see, which one's special? We have this is a double root, so this guy, something special happens here. This is a double root, so something special happens there. Okay, so it approaches this one from the top, and it can't get through here because that's a double root, and it can't get through here, so it's a double root, and it goes down, and so that's your picture there for the second question on number 3. Okay, let's do the last question on number 3. You've got x minus 1, x plus 2 squared, x minus 3 cubed. Your roots are at positive 1, negative 2, and positive 3. And this is a double root, so let's put a little note to remind ourselves it's a double root. This guy is a triple root. And the overall end behavior, let's see, this is 1, 2, 3, 4, 5, 6. There are 6 x's. If I were to multiply this out, I would have x to the 6. So x to the 6 is a smiley face, and so we're going to approach this guy from above, but can I go through? I can't go through because this is a double root. So instead of going through, we're going to bounce off of this. Okay, now we're approaching this one. This one's just a normal root, so we're just going to go through it just normally. And this one right here, this is a triple root, so I'm going to go through it, but I approach it with style, with pizzazz. I'm approaching it flattening out and then zipping up. And that's your graph. Okay, that is the third part of question 3. We're moving on to the second page of the assignment. You've got some graphs, and I'm going to do my best to draw these. They're not going to look as good as they do on your paper, but whatever, we'll do our best. This is 1, this is 4, this is -1. And your paper, drawn much better, looks like this. You hit that guy, you hit that guy, you flatten, and like that. Okay, so that -1, we're going to flip the sign, x plus 1. That +1, we're going to flip the sign, -1. That +4, we're going to flip the sign, -4. Now for the multiplicities. This is normal, so nothing happens there. This looks like a double root because it bounces off it. This looks like a triple root. And so this is one potential polynomial. There could be others. For example, there could be some number in front of it like 10. We wouldn't know because there's no scale on the y-axis. Okay, let's go and do this next one. You've got -1, you've got 1, and you've got 4. And it goes up through here. It flattens around in that neighborhood, goes down, and then it comes and it flattens around in that neighborhood. So that -1 flips to +1. That +1 flips to -1. That +4 flips to -4. Now this right here, that is looking like a triple root. And this guy, that flattening, also a triple root. Okay, and, oh, you know what? Go back. I forgot. This one, I made a, no, that's right. Sorry, I thought I made a mistake. Okay, no, that's all good. And then we've got one more graph. The graph is going to look like this. We've got -1, we've got 1, and we've got 4. And it goes up through here. It bounces off the 1, it bounces off the 4, and keeps on going. So our roots, x plus 1, x minus 1, x minus 4. This is a double root, so squared. This is a double root, so squared. Okay, question number 5. Question number 5 says, sketch a 5th degree polynomial. So I'm going to pause. 5th degree polynomial is going to look like that. And then it says with a positive leading coefficient, and that's what we drew, so that's good. The polynomial has 2 negative real zeros greater than -3. So that's a lot to unpack. Let's look at our number line. So it has -1, -2, -3. So this is -3. It says it has 2 negative zeros, 2 negative roots that are bigger than -3. So that means they're bigger than -3, but it also says that they're negative, and so they're somewhere in this region right here. We've got to put in 2 zeros. So let's go ahead, and doesn't matter where, I'm just going to arbitrarily pick a couple of zeros there. It also says that one of those has a multiplicity of 3. Again, it doesn't matter which one we pick, I'm going to pick this guy. That guy's going to have my multiplicity of 3. And it says the polynomial also has one distinct positive real zero less than 4. So less than 4 means that way, but positive means that way. So something in that region, doesn't matter where, I'm going to pick one right here. All right, so the overall behavior is going to be like this. It's going to have a couple of zeros that are less than, or that are bigger than -3, but that are still negative, and has one over here. This one right here has a multiplicity of 3. So let's go ahead and start drawing. It's going to go up. We're going to flatten. And that is one ugly polynomial, but that would do the trick. Okay, let's go and do another one. Here, we have to talk about quadrants. It says solution starts in quadrant 2, ends in quadrant 4. What are the quadrants? Well, the quadrants start here. That's 1. This is 2. This is 3. And this is 4. So there are our 4 quadrants. It says it starts in quadrant 2, so it starts here, and it ends in quadrant 4. It ends there. It has solutions at -2, 0, and at 2, 0, and at 4, 0. Okay, so with that, we're going to start it here. It's going to come through here. It's going to come through here. It's going to come through here, and it ends So this is the end, this is the start. Starts in quadrant 2, ends in quadrant 4. All right, let's go on and talk about number 6. So this is talking about the conjugate pair theorem. What the conjugate pair theorem says is this. If you have some kind of polynomial like x squared plus 7x plus 10, and let's just pretend for a second that one of its factors was x minus the square root of 2. Now, there are no square roots in this answer. So if this were a factor, and obviously it's not, but if it were a factor, you'd have to have x plus the square root of 2. And why do they have to come in conjugates? Well, let me show you what happens when we multiply them out. If we multiply them out, that gives you negative square root of 2x. This gives you positive square root of 2x, and those two cancel out. Meanwhile, on the top, if I multiply this out, that gives you x squared, and if I multiply this, the square root of 2 times the square root of 2 is 2, and so then you get x squared minus 2. So what that means is if you have a polynomial with real coefficients like x to the 6th plus 3x to the 5th plus 3x to the 4th minus 10x cubed minus 1, those are all real numbers, and I'm factoring this. If I have x minus I have to have that come with the pair x plus I. I can't just have this, because if I just had one of those and I multiplied it out, then that I would appear in those guys. And there are no i's in there. The reason there are no i's in there is because they would have done this kind of thing. Negative ix, positive ix, and canceled out. So if you have something weird, you have to have its weird friend, right? So think of you being weird, think of your weird friend. Things that are weird are like 3 plus the square root of 2. Now the conjugate would be 3 minus the square root of 2. What if it was just the square root of 2? Well, the conjugate's negative square root of 2. What if you have 6 minus I? Well, its weird friend is 6 plus I. So just remember, weird friends have to come in groups of 2 so that the weirdness cancels out. All right, so let's go and actually answer the question in 6. You have these as zeros or roots. 2, 3, negative square root of 13. Well, what does that mean? That means that the polynomial has x minus 2 as a factor, x minus 3 as a factor, and x minus negative square root of 13. In other words, x plus the square root of 13 as a factor. Now this is a weird one, so we have to have its weird friend, x minus the square root of 13. That means that this polynomial, the lowest degree it would have would be 1, 2, 3, 4 x's. So this would have to be x to the 4th, or it could be greater, right? There could be other factors in here we don't know about, but the lowest degree, the smallest possible degree, is 4. Okay, this next one, you have negative 3, you got 5, 2, square root of 5, 7, and you have 3 minus I. Okay, so this one is normal, this one's normal, this one's normal. This guy, though, is weird. So we have to put in its weird little friend right here. And then we've got this guy is normal. Oh, this guy is weird, so we have to add its little weird little friend, 3 plus I. Okay, so then if I was to write this polynomial out, I'd have this. I'd have x minus 3 would turn into plus 3, x minus 5, x minus 2, x minus the square root of 5, x plus the square root of 5, x minus 7, x minus 3 minus I, and x minus 3 plus I. And that would be the polynomial. So what degree is that? 1, 2, 3, 4, 5, 6, 7, 8. I think that's 8, unless I'm counting wrong. 1, 2, 3, 4, 5, 6, 7, 8. Yep, 8th degree polynomial. Okay, moving on to question number 6. We are talking about what's called the rational roots theorem. Rational roots theorem says this. If you have a polynomial that is ax to the, doesn't matter, plus dot, 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 b, then this can be expressed as a polynomial with a bunch of those guys. Okay, now how do we know what is going to go there? What guesses can we make about that? Well, if this whole polynomial, if all these guys are integers, and that's an integer and that's an integer, all those coefficients are integers and those are all integers, then if this polynomial has rational roots, if, that's a big if because it might not, but if it has rational roots, the rational roots would be in the form factor of B over factor of A. So let's unpack that with an actual example here. Number 7. Our polynomial is 7x to the 6 plus 3x to the 5th plus 7x minus 12. So there's our polynomial. Now, again, the way this goes is you say factors of this over factors of this, and it's plus and minus. So it's going to be plus and minus factors of 12. You could say factors of negative 12, but that plus and minus is going to mean it doesn't matter, over factors of 7. So what are the factors of 12? Well, 12, unfortunately, has got a bunch of these. So let's write them out. We got 1, 2, 3, 4, 6, and 12. Factors of 7, just 1 and 7, plus and minus. So we have to do all the possible numbers based off of this. So the possible numbers are 1 over 1, which I'm going to write as 1, 2 over 1, which is 2, 3 over 1, 4 over 1, 6 over 1, 12 over 1. We also have these guys. We have 1 over 7. So I'm going to write 1/7, 2/7, 3/7, 4/7, 6/7, and 12/7. And these are plus and minus. So plus and minus 1, plus and minus 2, plus and minus 3. So taking a look there on number 6, which of those could be a root? Could 7 be a root? Let's see, is 7 in our list? And 7 is not on our list. So 7 could not be a rational root of this thing. So cross off 7. What about 3? Is 3 on our list? 3 is indeed. So 3 is good. What about negative 2? And we have 2. Remember, this is plus and minus, so we got negative 2. So 3 and negative 2 are good. What about 11? I don't see 11, so cross off 11. 13, cross off 13, cross off 8. So the 2 of those that could possibly be a root are negative 2 and positive 3. All right, number 7, again, rational roots question. It's saying you have 6x to the 4th plus 2x minus 12. It says list all the rational roots. So factors of 12, 1, 2, 3, 4, 6, 12. Factors of 6, 1, 2, 3, 6. So brace yourself. Have a nice snack, maybe something sustaining, maybe with oats or something, because you got to use your energy on this one. We got 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. So I'm just going to write 1, 2, 3, 4, 6, 12. We also have those same numbers, 1, 2, 3, 4, 6, 12, all of that over 2. So I'm going to put all those over 2. We also have those numbers, 1, 2, 3, 4, 6, 12. We have all of those over 3. And finally, we have those same numbers, 1, 2, 3, 4, 6, 12, all of those over 6. And all of these, this whole big thing, and this whole big thing, this is all plus and minus. Okay, so we have positives and negatives of all those numbers. Now, we're not done yet. We got to go through and get rid of duplicates. 2 over 2 is the same thing as 1. 3 over 2, that's good. 4 over 2, that's 2. 6 over 2, that's 3. 12 over 2, that's 6. So we got rid of some of those. 1 over, that's good. 2 or 3 over 3, that's the same thing as 1. 4 thirds, 6 thirds, well, that's the same thing as 2. And 12 thirds, that's the same thing as 4. Over here, 1/6, 2/6 is the same thing as 1/3. 3/6 is the same thing as 1/2. 4/6 is the same thing as 2/3. 6/6 is the same as 1. 12/6 same thing as 2. And so now what's left are our unique possible rational roots. Okay, let's do one more, because that's about all I can take. We got 5x squared plus 4x minus 12. Again, we're on question number 7. Rational roots. Roots of 12 are 1, 2, 3, 4, 6, 12. Roots of 5 are 1 and 5. And so my answers are going to be 1, 2, 3, 4, 6, 12. 1, 2, 3, 4, 6, 12. But now all of those guys are over 5. And all of this is plus and minus, and checking for duplicates, and I'm not seeing any, so this would be your final answer. That last one on 7 I'll leave for you guys. Okay, now question 8 is some kind of tricky questions. These are just for my honors sections. So question number 8, let's look at it. you've got x cubed plus x squared minus x minus 1. And it says to completely factor this polynomial. Now we're going to apply the rational roots theorem. The rational roots theorem says that if this thing has rational roots, they will be in the form factors of 1 over factors of 1. So the factors of 1 are 1, and the factors of 1 are 1. So the possible rational roots are plus and minus 1. So that's nice. It's a pretty small field of things. So we're going to attempt to divide this thing by x minus 1. Let's see if x minus 1 is a factor. In other words, let's see if 1 is a root of the polynomial. So to test if 1 is a root of the polynomial, we got our long division set up. We're going to bring that one down, going to multiply, we're going to multiply, we're going to add, and that works. And so what this means, let me clear off some space, is that when I divided that polynomial by x minus 1, I ended up with this polynomial, x squared plus 2x plus 1, which I can further factor into x plus 1, x plus 1. So that means the full factorization of this polynomial, let me actually write it this way. Let's think about it this way. I can, at this stage, I can multiply both sides by x minus 1. I'm going to multiply this by x minus 1. When I do that, that cancels out, and I have this. I end up with this all by itself. This comes down here, x cubed plus x squared minus x minus 1 equals x squared plus 2x plus 1, x minus 1. And we can further factor this into x plus 1, x plus 1, x minus 1. Which, if you want to be fancy, you can write that as x plus 1 squared, x minus 1. Okay, let's go on to this one. You've got x to the third plus 4x squared minus 4x minus 7. And it says, hint, there's only one rational root. So only one rational root. Well, what that means is this. Here's our nice, happy rational root. It's a third degree polynomial. Maybe it does something like this. And this is our nice, happy rational. And this right here is crazy. Maybe that's pi. Maybe it's the square root of 11. And this one right here is crazy. That's one possibility. You have one rational root, and then you have two crazy square root, or pi's, or other things. Now, another possibility we're going to find out here is maybe it does this. Maybe this is our rational root, and then the others are imaginary. So we don't know right now. We're going to just attempt this and work this out. So according to the rational roots theorem, because this is -7, factors of 7 are 1 and 7, and this is a 1. And so the two possible, well, there's actually 4. We could have plus and minus 1 and plus and minus 7. We don't know which one's going to work, so let's just start with, I don't know, I'm feeling good about 7. Let's try 7. So trying my synthetic division, 1, 4, -4, -7. Bring this down as 1, I got 7, I got 11, I got 77, and at this point, I give up. So I have given up with 7. Let's try -7. So if I try -7, let me go in here and erase these. If I try -7, that goes down, that's -7, that's going to be -3. That's going to be +21, and I'm already seeing this probably isn't going to work out for me. Okay, so I have gotten rid of 7 and -7. Let's just try 1. So let me erase this. And I'm going to try 1. So if I try 1, 1 times 1 is 1. That's going to be 5. That's going to be 5. That's going to be 1. That's going to be 1. -6, that doesn't work. Let's try -1. That's going to be -1. That's going to be 3. That's going to be -3. That's going to be -7. That's +7. And finally, we got it on our last possible option here. So that is a factor. Now again, what does that even mean? Let me clear off some space. And let's just explore what that means. What did we even do with our long division? What's even the purpose of life? I don't know. Let's think about this. We just divided it. That -1 means that x plus 1 is a factor. If we divide that by the factor x plus 1, we get this polynomial, x squared plus 3x minus 7. Now, let me erase this. And let's see how we can use that to further factor our polynomial. If I multiply this side by x plus 1, and I multiply this side by x plus 1, then those cancel out, and now I know that this polynomial can be expressed as, well, first of all, it's x, we got their polynomial. It can be expressed as x squared plus 3x minus 7 times x plus 1. So we've already gotten it a little bit factored. Now this is a quadratic, so I'm going to factor that quadratic. So I'm going to go back and I'm going to say, hey, when I factor quadratics, I say, looking for numbers that multiply to be -7, that add up to be 3, and it's not looking like anything's working. So in order to factor something that's otherwise unfactorable, quadratics, we have to use the quadratic formula. So using the quadratic formula, we have -3 plus or minus the square root of 3 squared minus 4ac all over 2a. -3 plus or minus 9, negative and negative make a positive. 7 times 4 is 28 all over 2. It's going to be -3 plus or minus the square root of 37 over 2. So what does that look like? If I was to graph this on a graph, let's just think of the quadratic, okay? We're only graphing, what was that? X squared plus 3x minus 7. X squared plus 3x minus 7. If I just graph this polynomial, what do those roots look like? Well, one of the roots is over here. It's going to be -3 plus the square root of 37 over 2. One of the roots is -3 minus the square root of 37 over 2. So how do we write these as factors? For this one, let's just review something that we have here. What if they were nice, happy numbers, like 3 and 5? If they were nice, happy numbers and the graph went through them, like, what's that guy? Went through them like this, then we would say this polynomial is x minus 3, x minus 5. See how we're doing the minus there? So that means, what if this one was a -3? Then we would do x minus -3 and x minus 5. We're subtracting those away. So if I have a polynomial here that goes through those guys, we're going to say that factor is x minus, and prepare yourself because this is going to look a little crazy here. We're going to write that whole thing. And then this is going to be x minus, again, we're going to write that whole thing. And that is the answer to that thing. Well, we had one other root, and our other root was up here at that guy. And so now we can write our whole answer as that with an x plus 1. So it comes here, and maybe the 1, or maybe -1, I can't remember where -1. Let's say -1 is right here. Then it'll kind of zip around like that. Okay, so hopefully you guys are still alive after that one. That one's intense. Next one. It says, this is question 9. It says, prove that x squared minus 2 has no rational roots. Now, there's two ways of doing this. The first one is to apply the rational roots theorem. The rational roots theorem says that if it does have rational roots, they would be the factors of 2 over the factors of 1. So it'd be 2, -2, 1, and -1. And we can apply synthetic division to each of these and see that it's not going to work. So if I try -1, we have 1, 0, -2. 1, we multiply that, that's going to be that, that's going to be 1, and we get a remainder. And you get remainders for all of those things. And so you could just say, by trying all of the possible rational roots and showing that none of them work, that this thing has no rational roots. Now there's a better way to doing it though. We can factor this using the difference of squares and say, well, that's what this polynomial is. And so its roots are the square root of 2, negative square root of 2, neither of which are rational, therefore it has no rational roots. Number 10. Number 10 says this. You have this polynomial, x to the 4th minus 2x cubed plus 2x squared plus mx plus 2. And it says divide this by x minus 2 such that it is divisible, meaning there is no remainder. So let's do the synthetic division. And we got 1, -2, 2, m, and 2. Well, let's see what happens with that m when we run our synthetic division. That's going to give us a 0. That's going to work that. We got 4. Now, how am I going to add these together? Well, I'm just going to have to call it m plus 4 for now. And then right here, multiply that by 2, that's going to be 2m plus 8. Now it says that it's divisible by x minus 2, meaning that there is a 0 remainder, and that's the trick. There's a 0 remainder. That means 2 plus 2m plus 8 is 0. And I trust that from here, you guys can solve that. 10 plus 2m equals 0, and you can find m that way. Okay, last question. It says, use the remainder theorem to evaluate this thing, and the thing is x to the 4th. We're on question 11. X to the 4th plus 5x cubed plus 15x squared plus 8x minus 10. All right, this is p of x, and we want to find p of negative 2. So the difficult way of doing this, the time-consuming way, is to plug in negative 2. And you can tell that that would be very computationally expensive, right? That would take a lot of resources to compute that. Now the trick is we can also divide this by the factor x plus 2. In other words, we can just see that negative 2. We can synthetic divisionify this. 1, 5, 15, 8, negative 10. And if we run the synthetic division, what is the remainder will be the result of that expansion. So let's bring that down. That's going to be negative 2. That's 3. That's negative 6. That's 9. That's negative 18. That's positive... Wait a second. That's right. No, negative. Negative 10. That's going to be positive 20, and you end up with a 10. So that means when we evaluate this polynomial, it should be 10. Just for fun, let's go ahead and do that here underneath. So negative 2 to the 4th is a positive 16. 2 to the 3rd is 8. That's going to be 40. 2 to the 2nd is 4. 15 times 4, that's going to be 60. That's going to be negative 16. That's going to be minus 10. And does this work? That turns into, hang on. That turns into 100. That turns into, wait, that gets 90. I think I did something wrong. So we got x to the 4th plus 5x cubed plus 15x squared plus 8x minus 10. If we evaluate, oh, I forgot the negatives. You're probably screaming, I just can't hear you because, I'm before you in time. But that's going to be 16. That's going to be negative. That's negative 40. That's going to be positive 60. That's going to be minus 16 minus 10. All right, so let's see this. We got, that's going to turn into 20. Those cancel out, and 20 minus 10. Yep, that does give us 10. All right. So you can see that we can get 10 by directly subbing the number in, or we can also evaluate a polynomial by doing synthetic division, and the remainder will be that. Okay, that's probably enough for today. Have fun studying, guys.